It's easier to learn science than people imagine. So I guess my childhood, I grew up in Arkansas, just outside Little Rock. So I grew up on a farm, not really a working farm, but horses, dogs, cats, that sort of thing. And it's about 10, 12 acres. And really grew up, my parents were both engineers. So always kind of very practical, very oriented in like doing this to make something, to build something. And I at some point, and I feel like it was probably 10, 12, somewhere around that age, kind of started to fall in love really with science and especially physics. And I got very, very excited about physics, would read everything I could. I was at, just the right age that you could read everything on the internet. I was born in 85, so, by the mid-90s, the internet was going well, right? And, everyone my age remembers the AOL dial-up sounds. And I really fell in love with physics. And I remember my parents being a little bit worried about whether I could really get a job doing science. And it wasn't such a thing in Arkansas, but they were very supportive. And so I loved it. And I remember just reading this and reading and really loving also kind of this golden age of physics, this time in which kind of we discovered quantum mechanics and special relativity and all these extraordinary things that we almost had no right to know, this kind of beautiful facts about the universe. And so yeah, I was really, I don't know, I just somehow loved it. And I grew up, in a lovely childhood in nature, doing all these things, loving mathematics, and it was a great time. Certainly my father, who worked at this company, BEI, that made really impressive, basically parts for satellites and other applications, like a part on the Hubble, and being like next to this extraordinarily, someone who worked on these really, really important things, I think was important. As I went into college and I was a physics major, I think really, there was a professor, Med Webster, who taught actually the lab section for modern physics, was one of the first physics classes I took. And he was just like, so kind of precise and insightful. He knew so much about physics, but he also, if he asked you a question, you gave the right answer, but you weren't sure, he would know. And there was this just really, to me, like this kind of perfect gentleman physicist who was really embedded in this, was really doing these things. And I fell in love with that. And that really through college. And then I think maybe the other really formative experience actually is I went to graduate school for a PhD originally in physics, and it didn't quite grab me and exactly what I was working on. And my advisor was a really, good person, but the research didn't grab me, and I dropped out of my PhD to go basically get a job because it was too late to apply to American grad schools when I just decided to drop out. I thought I might go back, maybe do math, maybe do physics and something else. And I ended up working at this company, D.E. Shaw Research, and run by David Shaw. And they were doing biology on computers, and they were really trying to simulate how proteins move. And I remember what was absolutely formative is they were deadly serious. We're trying to do this really hard computational problem so we understand proteins, so we can, contribute to cures for these diseases. And we are studying this protein, and specifically this change in this protein, because we can connect it out to lung cancer and everything else. And it was just kind of this transformative thing that you can, for one thing, get together in a team and really try and solve a really hard problem, not just kind of increment it a bit. And we're doing this because it will matter, because, it's the difference whether people go home from the hospital. And I think just this whole connection from what I, loved and I thought I was good at, and like the world of mathematics and atoms and computation. And I love these things out to health and its real impact on society. And I fell in love with that. And it was absolutely kind of formative. And then I went back to grad school in chemistry almost by accident. That's another story you should ask me about. But anyway, and really was like, let's use computers to solve biology problems. This will really matter and people will care. Twice in my career, I've had complete accidents. I started with a plan, and the plan was to be a laws of the universe physicist, and I kind of disabused myself of that. The timescales were really, really long. A story I like to tell, it's a true story, is I wanted to be originally a high energy physicist. And I did some undergraduate research with there's some really good high energy groups at Vanderbilt where I did my undergraduate. And we got lunch one day and I said, this experiment we're working on, when is it going to turn on? This was the BTEV experiment. And the professor sitting next to me said, well, I might be retired by then. It's going to be a while. And the professor sitting next to him says, I'm a bit older. I might not be around when this turns on. And I just decided I wanted to do a little more immediate science than that. I didn't have quite the patience. It's important, but I didn't have the patience for that. And so that was kind of the first kind of shift. And I go to grad school, or my original PhD, and then I drop out. And I actually applied for finance jobs, thinking I was going to work a year or two as an unemployed physicist. And I end up instead working in computational biology and falling in love with it. But then the kind of third bit of absolute randomness is that my wife, Carolyn, who's here with me today, she decided she wanted to go to graduate school to get a PhD as well in genetics. And I was going to do what I had kind of intended in physics or math, I think more physics. And so we all applied to grad schools. And if you and your wife are applying to the same applying to grad schools, you need to apply to the same places, right? Because it's like 5-6 years, and I'm not going to live apart from her for 5 or 6 years. And we applied to all the same places, except one of the places was Chicago, but I missed the application deadline. It closed at 5. I thought it was going to close at midnight. And so I missed the deadline to Chicago, and I said, what's the chance the one place I want to go is Chicago? And so a few months later, my wife has a great offer from Chicago Genetics. That's by far her best offer. I have great offers elsewhere, but nothing in Chicago. And for like a month, I try and convince Chicago Physics to let me apply late. And they quite reasonably said, no, maybe next year, that kind of thing. And I'm telling the story to a coworker. And he says something like, well, do you think you could be a chemist? I know this professor in UChicago chemistry that I overlapped with in my postdoc. And I said, well, and at this point I hadn't taken a chemistry class since high school. And I said, sure, I can be a chemist. How hard can this be? Right? Whatever it takes to get me out of this problem. And so he must have said a very nice thing to this professor. And so I talked to this professor, and a week later or something, they say, we're going to open the application for you for one day, and then they pretty immediately accept me, and I became a chemist. And so I had to learn general chemistry 1 week ahead of the students for the class that I was TAing. But yeah, so that's the way I became a literal card-carrying chemist. And but apparently, I've now won the chemistry Nobel, maybe for biology, but it still counts. I think it's really, really important for scientists to know really well all the aspects of their work. I think it's not enough to me to bring together an interdisciplinary group of people where you grab a computer scientist and a biologist and a physicist or something and put them in a room. As a person, I think it's really, really important that you learn these fields, that you go talk to the people who are really good at it. I had these kind of formative experiences. For example, I learned computer science by going to computer scientist lunches and seminars and learning what they actually care about and how they think about it. And I think it's so much more valuable, and then I would go to biologists, to chemists. I think it's really, really important as a person to experience and find the experts in those fields and learn how they think and then bring it back to your work. And so we both work in interdisciplinary teams, but also build interdisciplinary people. And I remember when we were working on this project, we would run reading groups, which is quite common. This is where you would discuss some recent paper. And we made a pretty intentional decision that we would do either the reading groups, or about half and half, the reading group on the latest in computer science or machine learning, like what were the things people were really thinking about just from a computer science lens, or we would think about, biology and read recent biology papers. What do they care about? How do they think about it? How do they measure their data? And actually read less. We built the interdisciplinary ourselves. We kind of tried to get the best of those fields, and I think that's really important. And we started with a team that I was the most biological of the team, and I went from the worst biologists in my biophysics lab to the best biologist at the time the team started. And Catherine's a better biologist than me, and she came on later, although as a computer scientist. A team that was mainly physicists, computer scientists, etc., and taught them structural biology. And I think it's a fun way. I recommend it, and I think biology is such a wide subject that it's easier in some ways to learn biology than it is to learn, computing or AI, which have a longer progression to get to the edge. I came into AI from kind of the other side. I came from the simulation computing, like we will write down really proper laws of physics and then we shall simulate them. And that's kind of the story we tell. We'll write down the laws of the universe and then we shall play it forward like a clock, right? Or like some grand machine. But then when you actually go and do it, you find people adjusting stuff. It doesn't match reality. Let's change these equations. Let's make them simpler so we can compute them. Let's do all these things. And so like the way that people study nature isn't as clean as you imagine it coming as we tell people in school, even in college, that these are the laws and then we simulate them. It's really a messy empirical discussion with data. And when I was at my job at D. Shaw, we had these amazing computers for simulating. They built custom computers down to the computer chips themselves. And 100 times faster than any supercomputer in the world, 1,000 times faster than most at this narrow problem of simulating how proteins move. And then I went to my grad school and I didn't have that. And I didn't want to go. I was still interested in the same scientific questions, but I didn't have the same computational instrument as I had before. And so it became a really active goal. Can I replace with algorithms, with machine learning, what I didn't have in hardware, I was going to try and build with algorithms and ideas. And so that was my direction of travel into it. I think a couple pieces of advice I would give. One is simply that my path and the path of many other people isn't straight. People don't end up doing the thing they were trained to do. We're trained to do the problems that people knew how to solve in the past, not the new ones. So I think part of it is not being afraid to be a little bit myopic, to really go after the interesting thing tomorrow, to get that new skill. I think the other piece of advice I would really give is to meet many communities. Don't live within this narrow discipline and community. And I meet a lot of grad students who go to their lab meeting and then they go to the seminar of the department they're in and they learn a bit, but it's ultimately narrow. They never go to the department even, down the hall, or go and really see the breadth of science that's being done. And they miss the opportunity to import ideas and perspectives from all over. And it's easier to learn science than people imagine. I think it's like learning a language. Learning your second language is really hard. Learning your fifth is not so bad. As you kind of dive into more disciplines, you'll find you have this incredible kind of ability to learn that people don't realize that they've learned more about how to learn than they've learned about their subject. And that makes it much easier to pick up all these other things if you go after it. It's worth it. I think there's a couple perspectives of failure, and we fail on many scales. I like to say if 9 out of 10 of your ideas as a AI research scientist are failures, you're the most productive person I know. It's just incredibly hard. We have guesses about what to do, and then we learn from trying those guesses. The important thing about failure is to do it quickly. Actually, a lot of what I would spend my time doing with the AlphaFold team would be talking people into the smallest version of their idea. Because then everyone would come and say, I have a great idea, and they'll describe something and I'll say, but that would take 2 months. It will be 2 months for you to test that idea. It's so grand. What's the 2-day version of testing the same idea? And eventually, often you could come up with, well, if that works, then we can change this line from, a plus to a minus, and then see what happens, or add this term. And the important thing about failure is you do it really, really fast. If you just accept that you're going to have a 90% failure rate, and you should just accept that in machine learning, well, then you need to try, 10 ideas a month so you can have 1 success a month, right? So it really is about how fast can you fail? And I would also say that, it's about also, and I tell this to a lot of, young scientists, it's not about proving your idea could never work. A lot of people get obsessed at deciding whether an idea could work or never work. And it doesn't really work that way. You're just trying to figure out what you should do tomorrow. What has got the best chance of succeeding tomorrow? Often that's what you're doing today, right? You have the investment. It's a good idea to try it again, try a variant of the idea tomorrow. But really stop focusing so much on being right or wrong as taking the good shots that will ultimately lead to success, and being, very efficient with this precious resource we have of our time. You should always learn from your failures, and you should always learn as much as you can. And really good scientists that I've seen, and myself on a good day, learn a lot from the failures and the successes. They extract information about the problem, and it's not really a failure. The failure is when you learn nothing about the problem. And sometimes you do. You take your shot, it doesn't work, and you get on with life. But that's the important part, that you know more about the problem, that you've constrained the set of solutions or non-solutions. I would say, in terms of access, 2 things are really important. One thing that's really important is just a really clear description of how the thing works. And to me, that is the heart of the papers, that there needs to be a description of the thing that would let someone else build it and reproduce it. That's the soul of the scientific paper. It's also, I think, really important that scientists have access. And what access really means, and our open release of AlphaFold 2 as software was really important because the community built on it in all sorts of creative ways. I like to jokingly refer to it as off-label uses of AlphaFold, right? So we had a very clear goal and intention and problem we were trying to solve, right? How do we predict the structure of one protein from the sequence of that protein? And as soon as it was released, we saw this explosion of creativity in the field, of people doing really exciting stuff. Like almost immediately, someone posted on Twitter, if you take 2 proteins and stitch their sequence together with glycines, which is a standard thing to stick them together, it will predict how proteins bind to each other, 2 different proteins that bind. Oh, wow. And, someone else had another variant of that trick. And almost immediately, people started to explore and use their own creativity. And we see this a lot, actually, recently in finding new biology with this. And one paper I really love, published in Cell, they knew that there was some missing protein in how egg and sperm come together and make what's called the fertilization complex, right? How do they recognize each other biochemically? And they had a list of 2,000 proteins that are on the surface of sperm known from some other study. So they just ran all of those through AlphaFold to see which ones could AlphaFold stick up against this fertilization complex. And they found one clear hit, and actually another group in Sweden also found this hit. And then this group really tested it experimentally and showed that was the right protein. If you take it out, then the egg and sperm you won't have fertilization events, et cetera, doing the biochemistry of confirming this. But it's because they did 2,000 predictions, and you would never solve 2,000 protein structures, right? It's a year per structure or so. It's really doing new types of science because you have access. Part of what I think is important about open access is it lets people use it in ways the creators don't know about, haven't intended. And it's, there's so much biology. It's a tool. And, I like to say, on a really good day, maybe we're making structural biology as a whole 5% more efficient. That's extraordinary, right? That's really, really exciting. And of course, some people have absolutely transformative applications in their area, but as a whole, it's important to have access to these tools, that science as a whole gets faster. I think it's incredibly important for science to contribute to the world, to the problems, to, the incredible burden of disease, right? We have to. And why is drug discovery hard? It's not just because people don't spend money. They spend a tremendous amount of money on drug discovery. Drug discovery is hard because we don't understand biology, right? We need to understand the science of that to build the right medicines. We need to be able to ultimately, proteins, or how the cell moves atoms around on the nanoscale. And it's really, in a lot of the chemistry we want to do, nature does it better, does it more efficiently. And so how are we going to ultimately engineer that? How are we going to solve all these problems? Because it gives us a new type of technology, and that enables us to cure disease, to engineer new things. It's really, really essential. And I think it's, ever more, apparent to people after the pandemic, how weak we ultimately are in the face of disease, how challenging it still is despite all our investments and all our technology. I feel like I'm in this field, I think, for two reasons. One, maybe the biggest, is I kind of love it. I love this kind of challenge and uncertainty and just like trying to solve these problems. And I think trying to solve these beautiful problems of like, how do atoms move? How did nature evolve kind of exquisite systems out of randomness? I think that's extraordinary. And I think the other reason I particularly love being in biology is it's such a clear path to the end. It's such a clear path that if I do this work well, then someone who doesn't care about the laws of the universe, but might care, or does care that their relatives come home from the hospital. And that to me is deeply important. And it's so, I'm certain now that, maybe not yet, but in the next few years, that there will be people who live because of the work we did. And then not a direct drug from us, but the insights lead someone else to build a medicine, lead someone else to treat a disease, and that there are people walking around because I lived my life in the way I did. And that's humbling and gratifying. I think there are many possibilities from AI. I think one I'm really excited about, or kind of close to my area, is that we can meet the complexity of biology. Just biology is big, enormous, wide, right? There are 20,000 plus places in our DNA that tell you how to build a protein, right? And many of these have had incredible amounts of study by scientists. Many others haven't. There is so much in a cell that I don't see how we're going to get there with, kind of one at a time studies. We're going to need to measure lots of data. We're going to need to put this into models. We need to meet that complexity. So I think one of the big promises of AI is that we will understand how the cell works. And it's hard to see how we get there without it. And then we will have some idea of what happens when we do a treatment, that we will basically shorten this incredible and terrible cost of drug development because we understand the biology better. And if we knew, if we know exactly what to go after, I think it's more direct than right now we don't know what to go after. I think the other kind of big promise of AI in this field, and what David's work is justly rewarded for the Nobel, is that we'll be able to engineer proteins that will ultimately be therapeutics, that will possibly be the dominant therapeutics, and that we will treat disease faster and better. And so I think, local to my area, I think there's a real promise that AI will help us solve this scientific problem, hopefully others, and we don't know for sure. One of the things I will say is that we benefited from an incredible data source, the Protein Data Bank. It was collected over many, many years, and there aren't too many of those in science. So there is a question of how much further will we be able to push this? How many will we have a couple of problems that are transformed by AI and many others that got no faster? And then will those problems be enough to really deliver the benefits we want? We don't know yet. I think we should have a humility about it. But there is a promise that it can do quite a lot. And I think it's, this prize is also really exciting because it's a acknowledgement that AI solved a problem that, humans couldn't by any other means. And it's, maybe different in a kind from some of the work that's done with language models or image generators, where they're doing incredible outputs that look like a human could have made them, right? And that's the high compliment. But AlphaFold is about, building something, solving a problem that we had no other way to do it. It's not like well, other than experiments, but there's no way that you could do it without experiments. No amount of human thought or cognition is honestly any good at all at predicting the structure of proteins. There's no person who thinks about it real hard and then writes out the protein structure. So I think it's the promise that we will solve these grand scientific problems as well. Oh, my wife is so terribly important in my career. A counselor, an advocate, pushing me to stop doing the things I shouldn't and pay attention to the right things. I mean, I would not have been able to do this without Carolyn. She's extraordinary, and she unfortunately didn't get her PhD because the advisors kept leaving the university after a year and a half, and that makes me sad. But she's absolutely been behind me the whole way and extraordinary.